Welcome to this special episode of Frequency Matters, the RF Microwave Update series. I'm Pat Hindle, and I'm talking with Roger Hotchking, Director of Sales at Mercury Systems. Welcome, Roger.
Great to be here, Pat.
Mercury has developed this great direct RF technology. Can you tell us about that and maybe some details about the architecture of it?
Sure. Well, direct RF has been around for a little while now, but the performance levels are increasing. Each time we turn around, they're getting more powerful. What direct RF really does is it directly digitizes a high frequency RF signal that previously required a analog RF translation, frequency translation stage to acquire on a lower speed sampling rate A to D converter. Now the A to D converters are so fast that they can digitize the RF signal frequencies directly, thus eliminating that analog down convert frequency stage. So it's a real game changer in terms of software radio architectures for a lot of systems and very important for defense systems, radar and EW, most importantly.
And so, what are some of the advantages and disadvantages of direct conversion? Because I know it could consume a lot of power, maybe. And I think you're direct converting to 30 gigahertz now, which is amazing.
Yeah, we've got sampling rates up to 64 gigasamples per second. Input bandwidths are about up to 36 gigahertz signal frequencies. That is the highest frequency. But with a 64 gigasample or A to D converter, you can actually capture 30 gigahertz or more of instantaneous bandwidth, which is really remarkable. And in terms of the benefit, besides the benefit of not requiring the analog RF circuitry, which can be somewhat cumbersome and also limiting, it also makes your system a lot smaller. So it's cost of that extra circuitry, the space and the power of that excess circuitry. One of the challenges for direct RF is, what do you do with the fire hose of data that's coming off the data converter in order to be able to use it? Because with, let's say, 30 gigahertz of bandwidth at those high sampling rates, you have to have some pretty powerful digital signal processing resources behind it, capable of running at that sampling rate in order to extract the signal that you're looking for. Typically, it's a smaller bandwidth, a slice of that wide input bandwidth you're looking for. And so a lot of the direct RF data converters have digital down converters. Instead of having an analog down converter, you do it digitally and in real time, obviously, inside the hardware of most of these direct RF A to D converters.
And Mercury brings to the market some specialties like chip scale integration, and also you're using a lot of the open architectures. Can you tell us about that?
Sure. Well, we have a device called the RF SIP, which is a integrated version of a 64 gigasample per second A to D and D to A chiplet with a Versal ACAP processor, which is a AMD Xilinx processor, advanced with a multiple processing engines on board, including scalar, vector, and image processing, all on the same device, the same FPGA device, and coupling those very tightly, those resources to the high-speed direct RF data converters is really the magic in trying to keep the system size small and to reduce latency with that direct connection, to make total time from an analog signal in through a processing chain to an analog signal out, as you would need for, let's say, an electronic warfare application. Try to minimize that latency and maximize the throughput through that chain. So that's another major advantage.
And then how about the open architectures like SOSA?
Sure. So we have used direct RF at a smaller frequency, basically at 5 gigasamples per second with our RF SoC product line for quite a while. And in some ways, direct RF really just means fast A to D converters. And 5 gigasamples per second is relatively fast compared to what you could do, say, 5 years ago or so. So we've used the SOSA open architecture standard as a kind of a template for all of our new signal processing and FPGA boards, acquisition boards going forward. So that really was one of our first SOSA offerings, the RF SOC board, using that Xilinx part. Now going forward, we're using some Stratix FPGAs and direct RF solutions. Now these come from Intel family as a new vendor, different vendor compared as with the AMD or Xilinx family, which we have done most commonly in the past. So now with the new Intel family that's out, the Stratix 10AX, Mercury has a 3U OpenVPX card that was released last year that uses the same 64 gigasample per second data converters, but instead with that Stratix 10AX FPGA. Coming up, Intel has announced a new Agilex 9 family of direct RF products that will use, again, the 64 gigasample per second A to D converter. But now on the Agilex 9, which is a direct RF family of their latest MCP 1, 2, and so forth family of FPGAs that will do the processing, very high performance processing. I think it's something like 25 teraflops of processing, something like that. It's tremendous, and which you need at those very high data rates coming in. So that chip has been released. It's not fully being delivered right now, but we're working closely on a design that will use that in a SOSA aligned open architecture 3U VPX card. We're also developing a new product using the recently announced Analog Devices Apollo A to D and D to A converter, which sample at 20 gigasamples per second. And this gives you a lower bandwidth and sampling rate, but it does give you very high density so that for many applications that only require, let's say, signal acquisition up to 18 gigahertz, which covers a lot of military applications, to have a high channel count, lower cost per channel, and a more reasonable data rate for the processing that must follow the data converters. So we see a really nice place for the 20 gigasample per second family of Apollo data converters from Analog Devices that were announced in June of 2023, just this year, and will be available sometime during 2024. We've got a product line based on that, all ready to go. So what we're doing is we're taking the latest technologies we can get for direct RF devices from the vendors that make them, and we're putting them on open architecture cards.
Well, it sounds like a great approach. What applications benefit the most from this type of technology?
First of all, you have electronic warfare, where that very wideband, low latency capability is vital. And then you have phased array antennas, which really cuts across just about every kind of software radio application, communications, SIGINT, where you want that electronic beam steering capability by using phased array antennas. But it's especially important for radar as well, both the latency and the steerability of the radio beam. By doing that kind of an antenna, it makes these systems suitable for smaller size to be put in UAVs or in aircraft, where the antenna, a rotating antenna, just isn't practical. So a phased array antenna on the side of a vehicle or aircraft, or even a small unmanned vehicle, could be very important for maneuverability, size, space, mission length, and so forth, to be able to capture the information using that electronically steered array for directing the energy, both receive and transmit.
Well, great. Thank you very much, Roger, for talking with me today about your direct RF technology and how that's really influencing these applications. I'm sure this technology will do well in the marketplace, so we'll be happy to check in with you down the line. And to our audience, you can find more videos at videos.microwavejournal.com. Thanks for watching.